Okay, so all right. So moving on, what we want to do is that, so here is our oven, and here say oven plus collimator, and here is our first magnet, say Stern Gerlach 1, and the beam is coming out, and there's a beam going out this way, and there's a beam going out like that. So what we're then going to do is that we are going to block the lower beam. So we are just going to look at the beam which is going in the spin up. And then what we are going to do is that we are going to allow it to go through a second Stern Gerlach, magnet. Okay, I'm just not going to be very accurate about the geometry, and I'm just going to do like this. So this is then, but this Stern Gerlach 1 was pointing in the Z direction. But the Stern Gerlach 2, let's call it, say, SG2, not Stargate, okay? So the Stern Gerlach 2 is pointing in a direction which makes an angle theta with the Z direction. Okay, so we are going to get two beams again coming out of here. Now we want to determine the relative intensity of these two beams. Okay, and what we will see is that the relative intensity of these two beams depend on this angle theta. Okay, so let's first see how can we express, this beam, which is plus Z, in terms of this beam, which is plus theta, and this beam, which is going to be minus theta, right?
Sir, can we say minus since everything is already plus?
Exactly. That is the question. Okay, that's a very good question. So let's look at this beam. Okay, remember that this beam can be expressed in terms of a different basis, and this basis was that, this is my if this is my Z direction, and if this is my, say, theta plus direction, then we did the analysis. This state is going to be related to the plus theta and minus theta state through this cosine theta by 2 plus theta minus I sine theta by 2 minus theta. Do you agree?
Yes, sir.
Because why the minus? Because the angles are being reversed here. It's a very minor point, but I want it to be accurate. Okay.
Oh, I see. Yeah.
Yeah.
I can see.
So what I'm doing is that I'm expressing this beam in terms of the eigenbasis of a different operator, because in essence, what the Stern Gerlach 1 operator is, SG1 operator, that operator was where it was making an observation SZ. What SG2 is doing, it's making an observation in the n hat dot S direction. Okay, and that direction is that operator I'm calling S theta. Okay.
So can we further do the same thing with the plus theta?
Yes, yeah, we're going to do that. Yes.
Okay.
Yeah. Okay, so now what we can say is that, okay, of this beam, this, this is the amplitude for the beam to be in the spin up state, and this is the amplitude for the beam to be in the spin down state. So what is the intensity of the spin up state? Of course, it's going to be this amplitude squared. In other words, if I take this beam, this state, and I project onto this part, which means I take the inner product with this thing, and then I take it squared, mod squared, right? This is basically quantum mechanics, the Born rule, remember? And that is going to give me cosine squared theta by 2, right? So this is going to give me the intensity of this beam with respect to the intensity of this beam, okay?
Yes.
Okay. And now what we will do is that we will further block this guy. Now let's look at this expression. When theta is 90 degrees, what do we get? We get
What?
half,
Half, yeah.
right? And when theta is 180 degrees, we get 0. Let's see if these numbers make sense. When theta is at 90 degrees, that means that your incoming particles, they all had, they were all pointing in that direction. The spin was pointing in that direction, right? So, but if you're observing now in this direction, we know that this is going to be expressible in terms of this thing and this thing. And of course, half of it will be this and half of it will be this. Okay, the amplitude is 1 over square root of 2, 1 over square root of 2 mod. But if I take 180 degrees, then we are doing the observation. We are looking at, we are selecting for states in that direction, and we don't have states in any states in that direction, right?
Yeah.
Because what we're doing is that we'll be sending all the particles in that case to this beam. So nothing will come out here if you take 180 degrees. But if you take 90 degrees, half of them will go here, half of them will go here. Okay. So now let's go crazy and do another Stern-Gerlach. So let's put another Stern-Gerlach here. So this guy goes in through SG3, and SG3 makes an angle of phi with the initial z-axis, okay? Then we can say that, okay, if that is the case, then, things that come out here, again, we're looking at just this guy. If we just, let's block this guy. If you just look at the upper beam, its wave function is, it's going to make an angle theta phi, and we can express it in terms of the original. And of course, it's make an angle phi, so there'll be cosine of phi by 2 plus z, and then minus I sine of phi by 2 minus of z. Okay. So now we can say, okay, what ratio of this beam is going to be in this beam? We have expressed this beam in terms of this, the wave function, this basis, but we have not expressed this in terms of this or vice versa. But the information is there, and we can use quantum mechanics to easily extracted. Okay. Are you guys following so far?
Yes, sir.
Let me just recap the physics. Okay. So oven, stuff comes out. Sorry, stuff comes out not like that. Stuff comes out like this. First Stern Gerlach magnet SG1 goes like this, goes like this. We block the lower part. Then we have, another Stern Gerlach SG2 comes out, and we are blocking this thing. And then another Stern Gerlach comes out, come out like that, and we're blocking this. Okay, so now we want to relate. We have related this, the state of this guy in terms of these two guys, but we want to now express this in terms of this. So let's calculate, what part. Let's calculate this thing. Right, and okay, so we want to know, so we are just basically, calculating these two coefficients, right? And these coefficients are cosine of phi by 2 minus I sine phi by 2. Now, but we want to express, we want to find in the fraction of the plus theta beam that, that gets passed on to plus phi. So we want to know this inner product. Okay, and then we want to square it. How do we do that? Well, we use our fine, we m minus m plus, we do a decomposition of identity, because there's an identity operator in between these two states. And we use the fact that we can always express in terms of the z basis, where m becomes plus and minus. Remember decomposition of identity, the projection
Yes,
operator?
Mhm.
We're just using this. Okay, so if I do this, then I get two terms, and let me just write them as vectors. So one, we will get cosine of theta by 2 plus I sine of theta by 2, plus, because we're taking the complex conjugate here, and then inner product with cosine of phi by 2 minus I sine of phi by 2, which is from this thing. Of course, there's a component, there's a sum, and that's why we've written it like this. There's a matrix summation. So if I do this, I get cosine of theta by 2, cosine of phi by 2, and then I get a plus sign, sine of theta by 2, sine of phi by 2. And if I use my trigonometry, so I get cosine of half theta minus phi. So we find that the fraction of the second beam that gets passed on to the third beam is given by cosine squared half theta minus phi. Okay. Did you guys follow the steps?
Yeah, kind
Yes, sir.
of. I'll have to
It's
go through
almost
this again.
because there's a lot of, but every little thing is understandable, and you have to go back and follow the logic and see that you are getting the point. The details are important, but more than that, it's just that how the physical picture, you could have argued this physical picture without doing any quantum mechanics, without doing any formalism. You could have just said, oh, I'm just projecting this, I'm just projecting that. But what I'm trying to show here is that how the quantum mechanical, framework, the machinery automatically gives you the right results. Now, there's something interesting here. What if you didn't have the second, Stern-Gerlach apparatus? Then what would you get? You basically, so if I take the second angle to be 90 degrees, and the third one to be at 180 degrees, I still get non-zero result here, right? But if there was no second Stern-Gerlach apparatus, so there was nothing here, then what would I get? I would get 0 here. So if I didn't have this guy, then this whole thing would get blocked if this was at 180 degrees, because this whole thing would then be spin up in the z basis, and at 180 degrees it would just collect these guys, so nothing would go in this direction. It'll just collect the spin down, and since there is no spin down here, nothing will come up in the upper beam. So the fact that we are putting a magnet at 90 degrees in between suddenly makes it non-zero, because then we suddenly have in between a state which is again a linear combination of spin up and spin down. Sorry, here. Spin up and spin down. Okay. If you didn't have this one, then in the middle it'll only be spin up. Okay, so I think I'm not expecting you to get everything here at one go. We'll do a tutorial on this, as well as the homework.
Sir, is this similar to like that polarizing filter experiment where like
Exactly.
you two perpendicular ones and one like diagonal one in between?
Exactly. This is very close to that. Very close to that. Except that for the polarization filter, we are looking at waves. Here we are looking at particles.
Right.
That's in fact, I think there is a very nice video by either Veritasium or Minute Physics on this. Minute Physics, I think. I'll post that on Slack.